Hi everyone, I'm Dhruv, and today I'll be going over how we do problems in forward kinematics and also a little bit of the theory of forward kinematics. So I'm going to work backwards here, and we can start with our initial equation. And explain all these terms, how we get them, and kind of visualize how these terms change our transformation matrix. So the goal of forward kinematics is to represent a transformation from our base to end effector frame. And between our base and end effector, we usually have many joints. So each one of these terms represents a joint between our base and end effector, with S1 being the joint closest to the base and Sn being the joint closest to the end effector. So what we do with forward kinematics is how does a theta degree shift in our joint angle affect our transformation matrix. So let's dig a little deeper into that. Let's start with the equation set to all angles as 0. So what happens is these terms become 1 and our transformation matrix is equal to M. So what this tells us is that M is the 0 configuration transform from our base to end effector. This is typically represented as M equals some rotation matrix R, some rotation matrix R plus a translation component. And how this works is essentially if we have a vector x, multiplying it by M gives us a R x plus P, which accounts for the rotation of our frame and also the translation from our initial point to the new basis's location. So now we've covered the base frame, and this is our 0 configuration. Let's go a little bit more into detail on these terms. So essentially, what this term represents is a theta rotation on our axis, our screw axis of a given joint. Now these joints can either be revolute or prismatic. And this essentially just means this is a rotational joint and this is an extension joint. Our S is typically written as a screw axis omega and a velocity component V. And omega is the screw axis, also the axis of rotation essentially, and v is the linear velocity of our origin with respect to our screw axis. So let's kind of visualize this. If we look at this system with the square being our base frame, let's call this direction y and this direction x, which would make z out of the page. And let this dot be a revolute joint. And let the angle of rotation for this joint, or the rotational direction, be counterclockwise. Now, using the right-hand rule, we can tell that the axis of rotation is the positive z direction. So that makes our omega 0, 0, 1. And this is going to be in terms of our base frame. So 0, 0, 1 in terms of the base frame. And now, how do we calculate our v? Essentially, what v is trying to look for, if we draw a circle around our rotation or our joint, it's going to be the tangential velocity component of our origin. Now, how can we solve for this? If we have q, the location of our joint, this v just becomes q cross omega. And we can validate this with the right-hand rule as well. So our q would be in the positive y direction, and our omega would be in the positive z direction, which would make our v in the positive x direction, and that checks out with this rotation. And this v component is just the linear velocity. So now, how do we get from the omega and v representation to an actual transformation matrix? That's where our exponential matrices come into play. Now, what does this representation mean? This is essentially just the skew schematic matrix of S, which breaks down into the skew schematic of omega with v1 then 0. And we can just write this as 0, omega 3, negative omega 2, omega 1, 0, 0, and omega 2, where omega can be written as omega 1, omega 2, omega 3. Now, how does this help us? Well, what we can see is that when we represent a skew as an exponential, we can calculate out that this comes out to e to the omega skew theta 0, 1, and then some function of theta v. Now, by the Rodriguez formula, we can find out that this term evaluates out to 1 plus sine theta skew of omega plus 1 minus cosine theta skew of omega squared, which is essentially just our rotation matrix. And analogously, this term simplifies to our translational offset. And this comes from the fact that any transform can be represented as a rotation plus a translation. Now we have essentially a representation in terms of a translational matrix or a transform matrix of a theta degree rotation about our screw axis. And that encapsulates a theta degree rotation about any joint in our system. Now, how do we put this all together? Let's do a practice problem. Oh wait, before we get to that, let's go over prismatic joints. For prismatic joints, since there is no rotational component, our omega is just the zero vector, and v is just 1 in the direction of extension. So with our axes being y and x, our v in this case would just be 0, 1, 0. So now let's do our example. So let this be our coordinate system, x in this direction and y in this direction, which makes z out of the page again. And we have our base located at this location, the origin, 0, 0, with a revolute joint located at 0, 2, so 2 in the y direction, and a prismatic joint located at 2, 2, 0, going in the x direction. And then finally our end effector located at 2, 2, 0 as well. And let the end effectors frame for this example also just be the same. Now that makes our M matrix pretty easy. That will just be 1, 1, 1, since there is no rotation. This captures our R matrix. We have zeros here. And our translational offset is 2 in the x direction, 2 in the y direction, and 0 in the z direction, which is just the expansion of this. And now we have to calculate, let this be S1, S2. Let's do S2 first because that's a lot easier. Since it's a prismatic joint, our omega equals 0 and our v is in the x direction, so that equals 1, 0, 0. So then that makes our S2 0, 0, 0, 1, 0, 0. And our S1, we know our omega is going to be a rotation in the counterclockwise direction, which we found to be in the positive z direction. And we also calculated out our v to be 2 in the positive x direction, if I'm not wrong. Okay, I don't think we calculated that, so let's just go through that. We know v equals q cross omega, which also is just negative omega cross q. And we can do that out, I, j, k. And our q is 2, 2, 0. And our omega is 0, 0, 1. So taking the I, we find that to be 2, I, which is just this determinant. Our j is 2, 1, 0, 0, which is just a minus 2. And we should have no k component as this determinant is 0. So let me just correct this. Our V matrix will then be 2, minus 2, 0. So now we have our S matrices. we have the second S matrix. And typically, theta 1 and theta 2 will be given to us. With this information, we will be able to solve for t, which should just be plugging in this formula. And we should have resources for this in the modern robotics library in Python. Now, an alternative way to do this is using the body frame, which is the end effectors frame. And in that situation, our t would be represented as m e s b2 theta 2 e b1 theta 1, where the b's would still be in the same orientation. So this would be b1, this would be b2, except we would calculate our omega and v in terms of the body's reference frame, or the end effector's reference frame. So that was a lecture on forward kinematics. I hope this was helpful. Thank you very much.